Okay, significant figures. Scientific numbers are reported in a very specific way. Every digit is certain, but the last digit is always estimated. And we do this very intentionally. When you make a measurement, there is always some uncertainty. You say, well, yeah, but the bathroom scale said blah, 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 0.7. It's exact. No, there's uncertainty in the last digit of a digital display. There is uncertainty in every measurement. And so scientists have come up with a way of communicating with each other that we all understand. And the problem is that beginning chemistry students have not been taught this, and so it's a very strange concept for you. It's a little bit like learning to play a new card game or something. There's some seemingly strange rules, so try to stay with me on this. So any number, any measurement that's written always has uncertainty. And so if this is a measurement, 45.872, the last digit is always an estimation. So we would say that these first 4 digits are certain and the last one is estimated. The estimated digit is important. It gives us some information, and we want to keep all the information we can. When this measurement was made, they were kind of guessing at the 2. They knew it was 45.87 for sure, and then they're pretty sure the next place is a 2. So it's an estimate. After that, we've got no clue what those digits are. The greater the precision of a measurement, the more precisely it was made, the more digits you're going to have, and the more significant, the greater the number of significant figures. So let's look at this balance. And looking over here, this balance has marks on it. We're going to look at the gram side because we don't use English units in chemistry much. So here's 0 and 10 grams, and there are 10 little lines in here, aren't there? So there are 1 gram markings on this balance. But we can estimate between. Okay, it's kind of small, isn't it? But we can see that the line here for measuring this substance is definitely more than 1 gram. It's definitely between 1 and 2. So in a measurement of 1.2 grams, the 1 gram is certain. We know beyond a shadow of a doubt it's at least 1 gram. Now where exactly between 1 and 2 it is, we're going to estimate. We look at that and we can say, well, yeah, it's not 0.9, it's not 0.8. What we do is we take that little tiny space and we mentally divide it into 10. If it was smack in the middle, we'd say 1.5. And then you kind of eyeball it and you're like, it's really close to the 1, but not like just barely off, and so we're going to call it 1.2. If you had 10 people record this measurement, you would get different answers. Some people might call it 10.1, some might call it 10.3, some would call it 10.2. Okay, there's uncertainty. We're not sure, but we have an idea, so we're going to keep that. And the pattern is, the rule is, you always write down the uncertain digit. 1 uncertain digit. Okay, so this reading here, 1.2 grams, what are the certain digits? Just the 1 is certain, and the 2 is uncertain. There's always 1 uncertain digit. Let's look at this one. I wish these were bigger. So this is a different kind of a balance, and it's really small. But if you can see, here's 0 and 1 and 2. So here the markings are at 0.1 gram, right? So we look at this and we see, look on here because it's bigger. Looks like it's 1.2 something. We can see between the lines. It's definitely between 1.2 and 1.3. If you can see the scale, can you see that? Okay. There's no uncertainty about that. It's between lines. And then we estimate the last digit. So we look at that and say, well, it's close to half, but it's a little above. So we maybe record it as 1.26. So 1.26 grams has two certain digits, the 1 and the 2, and the last one is always uncertain, the 6. Do you have any questions yet? This whole significant figure business makes a lot more sense if you understand where the uncertainty's coming from and how these measurements are being made. What we do is we always estimate between the lines. So I'll remind you in lab, read between the lines. Read between the lines. Because the tendency for students is they'll say, well, that's 1.2. You've got more information there. You can see that it's more than 1.2. And it's less than 1.3. So let's take a guess at it. Okay? Here's another example. This one's maybe easier to see. Here's a thermometer. Temperature of the backyard in a hot tub. I almost said on a hot day. Could be either, right? That'd be, it's entirely possible in the backyard. This is degrees Fahrenheit, by the way. So how should we record this temperature? Well, we have to look at the measuring device and see what do those smallest divisions represent. Here's 100, and up here this is 110. So each of these lines then represents what? 1 degree. That means that we're going to estimate to the next place, the 10th. So we look at the mercury in here. There's 100, 101, 102, 103. It's between 103 and 104. So we're going to call it 103 point. And then we're going to estimate. Someone said 4. Looks pretty good to me. And this is degrees Fahrenheit. Now, someone else might estimate that at 103.5. Does that mean one person is wrong? No. It's an estimate. There will be some variation there. But if we just call that 103, we're throwing away information. Because we know that it's actually over 103. So any measurement that's written correctly will have uncertainty in the last digit. So if I see this and I see, oh well, they were estimating this 0.4, so probably what they mean is that this is their answer to within 0.1. It's probably between 0.1 above and 0.1 below. So it's probably between 103.3 and 103.5. If I just wrote 103 degrees Fahrenheit, that would imply an uncertainty of plus or minus 1 degree, meaning it was more estimated, less precisely measured. 103 says to a scientist that's between 102 and 104. But our thermometer gave us more information than that. And so this is not a correct way to write that measurement. Yes?
So if, let's say the bar was like directly on 1.34, could you write 103.40?
Yes.
Saying that that's your uncertainty, that you're pretty, that you
Yep.
know it's 4.
So what if it was right here? It looked like it was right on the line. Then what do we do? Well, we're still estimating the 10th place, and so we put a 0 there. So this one, we would write 105.0. It's a very good question. I'm glad you brought that up. So if it's right on the line, you still have to think, well, what are the smallest divisions? The smallest division is 1. I'm going to estimate the next decimal place. The certain digits are up to the 1 this is where the smallest places are, I need to have one more decimal place in there. And we'll go over this in lab as well. Any other questions? So significant figures are the digits in a correctly written measurement. They're all the certain digits plus one uncertain digit. So we need to learn how to look at a number and count the number of significant figures. So there are rules. And I think these rules are slightly different than what's presented in your textbook, because my experience is this makes more sense to students. They'll get you the same outcome. If you prefer the rules in your textbook, by all means, use them. We'll end up with the same answer. So rule 1, all non-zero digits are significant. So in these examples here, what non-zero digits do we have? Well, that's all the digits that aren't zeros. So the 1 and the 5 in there, and these two ones. So non-zero digits are always counted. The problem arises with the zeros. So did you know there's 3 different kinds of zeros? There's interior zeros, or trapped zeros, zeros that are on the inside of a number. There's zeros that trail at the end of the number, and then there's zeros that lead at the beginning of the number. So the interior zeros, and by that we mean zeros between two other digits, are always considered significant. So in these two examples, this 0 is an interior 0, and this is an interior 0. I am underlining the digits that the rule is talking about. I'm not underlining the significant digits. In 50.1, this is an interior 0. It's between non-zero digits. So those are always counted. Trailing zeros. These are zeros at the end of the number. We read from left to right. So the number's like a train. And the ones at the end, sometimes these are significant and sometimes they're not. These are the fun ones. If there is a decimal point written in the number, those zeros are significant. So 5.10, that's a trailing 0. There's the decimal point. That makes all the trailing zeros significant. 500.0, these are trailing zeros. Because of that decimal point, they are significant. If we have a number like 100 and there's a decimal point, you might say, well, that looks kind of weird. Yeah, it does look a little weird, because normally we would just write 100. But there is a decimal point that someone took the care to write down. Those are trailing zeros, decimal point in the number, those are counted. If we have a number like this, 20, no decimal point, that 0 is not counted, because there was not a decimal point. Doesn't matter if the 0 is before or after the decimal point. If it's on the far right side, if it's a trailing 0 and there's a decimal point anywhere in the number. Any questions? So I kind of jumped ahead. Trailing zeros before an implied decimal point are ambiguous. So this is being sloppy. And sometimes your textbook is a little sloppy, and I don't like that, but mostly they're pretty good. But when a scientist writes a number like 50,000, where's the uncertainty? Let's say you're counting the number of people that live in Visalia. And you say, oh, there's 50,000 people. I don't know what the population of Visalia is. Somewhere in that ballpark. You say 50,000. Did they really actually count every single person? Do they know that to the nearest person? I mean, even if you went out to physically count people and maybe even put a rubber stamp on their forehead or something to identify, yes, I've counted you, because people mill about and they go to the mall and they go to work and, they move. People may leave town in the process of you counting them. And so there's uncertainty in that number, right? Where does the uncertainty lie? We can't tell in a number like that. So what we're going to do is we're going to assume the worst. We're going to assume that all of those trailing zeros are not significant and that the uncertainty lies in that first one, the 5. We're going to assume that this is the estimated digit, the 5. So 50,000 written like that means between 40,000 and 60,000. That's just a ballpark number, right? We say the number 10. Oh, it's 10 feet long. Well, is that just kind of a guess? Do you mean between 11 and 12? Or is that between 0 and 20 feet? Do you mean it's exactly 10? It's ambiguous. So if there's no written decimal point, trailing zeros are not counted as significant digits. We avoid using these by using scientific notation. Because if we put the number 50,000 into scientific notation, what would it be? 5 times 10 to the 5th. Let's see, 5 times 10 to the 4th. So if we wrote it that way, we would definitely be saying uncertainty in the 5. If we wrote 5.00 times 10 to the 4th, then we're saying that there's uncertainty here and that we actually measured that to the nearest 100. In scientific notation, there are never trailing zeros without a decimal point. So scientific notation is great for avoiding these ambiguous zeros. And leading zeros are straightforward. Zeros to the left of the first non-zero digit are not significant. These are place-holding zeros. So they're just locating the decimal point. If we didn't write those zeros, would the number change? Yeah. 0.0005 would become 5. Those are not the same. Are those zeros important? Yes, they're very important. Do they reflect a measurement? No. Because if I measure something and I find out that it's 5.5 grams, what if I decided to put some extra zeros in the front? It's still 5.5 grams. Does this imply that I measured it more precisely? No. That's just stuff. Okay, so what are these zeros here for? To hold the decimal place. What happens when we put that number in scientific notation? Leading zeros go away also. That becomes 5 times 10, 1, 2, 3, 4, to the minus 4. We don't need those zeros anymore. So these leading zeros are not counted. Over here, 0.0153, those leading zeros not counted. So now that we've gone through the rules, let's look at just these last two. Say, well, how many significant figures are in that number 0.0005? 1. And how about in 0.0153? 3. Those leading zeros aren't counted, and so it's just the non-zero digits in those examples. Then we have to talk about exact numbers. Exact numbers, for the purposes of significant figures, we just think of them as having an unlimited number of significant figures. So how can you come up with an exact number? Well, this could be exact counting of discrete objects. Okay, I can count the digits on my finger, on my hand. 1, 2, 3, 4, 5. There's exactly 5. Okay, you can count your children. I have 6 of them. Still can't believe that sometimes. 6. Oh, good grief. It's awesome. It's wonderful, but yeah, birth control doesn't always work. There's exactly 6 of them. It's not 6.5 or 5.9. It's exact, right? So when we count discrete objects, Now this breaks down when the counting becomes too many objects. Like if you're trying to count 50,000 people, okay, that's going to be a little more challenging. Where does that break down? Well, that's kind of a gray area. We're going to try to avoid gray areas. That's the nice thing about an introductory course. We can just stick with the more concrete stuff. So in general, if you're counting something, it's exact. Integral numbers that are part of an equation. Integral, meaning integers, whole numbers. So the radius, the diameter of a circle is twice the radius. So the diameter equals 2 times the radius. 2 is an integer as part of an equation. The diameter of a circle is exactly twice the radius. So that's an example of an exact number. Defined quantities are exact. And defined quantities we mostly see in conversion factors. Some conversion factors are defined and others are not. You think of 1 foot equals 12 inches. A foot and an inch are defined in that way. That relationship is exact. I'm trying to think of something else. I think it's 1.06. I think, this is probably going to be wrong. I think a quart is 1.06 liters. But a number like this, where we're going between the English system and the metric system, almost all of those are not defined. And so those do have uncertainty in them. So a number like 1.06, how many significant digits does that have? 3. The 1 and the 6 are givens, because anything that's not a 0 you count. The 0 is a trapped 0, and all trapped zeros are counted. So exact numbers. So here's some examples. How many significant figures in each number? 0.0035. 2. Okay, that's got 2. Leading zeros are not significant. How about 1.080? 4. Okay, so it's the trailing zeros that often mess us up. Trailing zeros get counted if there's a decimal point, not counted if there's no decimal point. So this number has a decimal point. Do we need this guy to hold a decimal place? No, because there's an actual decimal point to hold it. So why would we write that? Because that was our estimated digit. We think it was right on that line. 2,731. 4. 2.97 times 10 to the 5th. 3. Didn't specifically mention this, but with scientific notation, we're only looking at the decimal part, because this is the place holding zeros part. That's what moves the decimal place around. The nice thing about a number written in scientific notation, all of these digits are going to be significant, because there will never be any leading zeros, because the first digit has to be something other than 0. And if there are trailing zeros, there will be a decimal point. So in scientific notation, you count all of those guys. How many times did I underline that? Okay, 1 dozen equals 12. I'm hearing 2. If you have a dozen eggs, do you have 12 and a little bit? No, you have 12. Dozen is a counting number, right? This is a defined quantity. This is an exact number. So if you're pressed to say how many significant figures, it would be infinite. Because it's exactly 12. You count marbles. right? 12 marbles. Practically speaking, you can't get part of a marble, right? I know extremes, you can break marbles, you can cut them up, but 12 marbles. Not 13, not 11, it's exactly 12. So you could say 12.000000, and however many zeros you put out there, it would be correct. Okay, 100.00. 5. I value people willing to state answers, okay, even if they're not correct. Because when people state incorrect answers, that gives me a clue as to what you're thinking about and helps me to explain better. So 3, I can see why someone would guess 3. But let's look at those zeros. There's only one kind of zero there, they're trailing. Okay, they're not trapped between, they're all trailing. And so they are either all significant or none of them are significant. They're all significant because of the decimal point. So if there's a decimal point, you count all the trailing zeros. No decimal point, none of the trailing zeros. So then the next number, 100,000. 1. There we have trailing zeros, but there's no written decimal point. So that is an ambiguous number, and we're going to take the worst case approach and say, well, we'll just assume that all of those are estimated then. That it's 100,000 to the nearest 100,000. Because we don't want to take a number like that and assume it's to the nearest 1 and do calculations assuming that that number was very carefully measured when in fact it wasn't. And base our whole calculations and all of that on that. We don't want to do that. So any questions about these? This is something that is important. Now, I'll tell you things like that throughout this semester. Understanding significant figures is important. Can you pass the class without understanding significant figures? Yes. Yes, you can. Be pretty tough to get an A, though, because you're going to miss points on exams and stuff. But this is one of those things I want you to try. I want you to give it a good shot. But sometimes in life, we kind of have to cut our losses, right? You can't do everything. Okay, I can't be a good chemistry instructor and a good mom and a sane person and keep the house meticulously clean, right? Not possible. So guess which one goes? The sanity? Sometimes. No, mostly it's the house. My house is a mess. And it drives me crazy. But you know what? I just can't do it all. And sometimes in life, you just can't do it all. In fact, almost all the time. So in this class, I understand you have other classes you're taking. Some of you have jobs and families and stuff going on. So I'm going to periodically tell you, okay, if you're not getting this, this is one subject that it's okay to let go of. Okay? But don't dismiss it before you give it a shot. Okay? So try to get this down. There will be questions involving significant figures on the first exam. So I think you should definitely keep trying on this one until the first exam. And if it still is not making any sense to you, you have my permission to just kind of not worry about it anymore. Help me out here. Is this the same section or is this a different one? I think it's the same one. 2.4? I think it's the same one. I could always split it later, but I never do. Okay, so why are we doing all of this? This is so that when we use measurements in calculations, we don't end up with crazy numbers. Okay, when we use numbers in a calculation, we're going to round that number to reflect the number of significant figures in the data. So if we have multiple steps, sometimes you have to take two numbers and add them together and then divide them by something else and then raise them to an exponent or who knows what. We're only going to round the final answer. We really don't want to round off each individual step because that introduces its own form of error. It's called rounding error. So we want to avoid that. So we're going to have some more rules. So multiplication and division are related mathematical operations. They are opposites of each other. And so they share one rule. Adding and subtracting has another rule. So if we have two numbers that we're multiplying or dividing, the answer to that is going to have the same number of significant figures as the number, the factor with the fewest. Okay, and usually when we say things in words like that, it just does like, what? So examples are really, really important. So let's look at this first example. 5.02 times 89.665 times 0.10. There's the answer that the calculator gives. That's not what we're worried about here. We want to know how should we round that number off so that our result reflects how those measurements were made. We don't want to say, oh, well, it was about 10 this, and oh, I think there were 50 of those, and then come up with this answer that's 5.9376 or 7253. Because if we show that answer to people, they're going to say, oh, wow, they measured that really, really carefully. They know this very exactly. When in fact, we were just kind of ballparking everything. Okay, it's a little bit like, you think of a large institution and budgets. Okay, so they say, well, it's going to be about, $20,000 for this program and about this and about that, and they crunch all the numbers and, okay, well, we need to take in $5,273.47 every hour, and then we'll meet our budget. It's ridiculous, okay? Because the whole budget itself is based on very round numbers. And so that's what we're trying to avoid, is this craziness of extra digits. So we've got these three numbers we're multiplying. The rule is we're going to look at each number and figure out how many significant figures does that number have. So 5.02, how many sig figs does that have? That has 3. Oops. What did I do? There we go. Okay. Sometimes things happen on here that you don't see, so I'm not losing my mind. I already lost that. 3. And 89.665. That's 5. That one's easy because there's no zeros. Pesky zeros. 0.10. 2. Very good. Okay. The leading zero doesn't count. The trailing zero does because there's a decimal point. Now this is the hard part. Which is the smallest number, 3, 5, or 2? 2. Okay. The smallest number. That means we need to round our answer to 2 digits. So the 4 and the 5, we're going to keep 2 digits. We have to be careful when we round that we round correctly. So we're going to be getting rid of this 0. If that number is less than 5, we round down, because 45.01 is closer to 45 than 46, right? But if that 0 was like a 6 or a 7 or something, then we'd round up, okay? And I know that they taught you how to round numbers in elementary school. You may have repressed it, but if you work on it, you can channel it out again. So we're going to round that off to 45. Any questions? Yes?
Was 45.0 wrong?
If we're looking at significant figures, yes, 45.0 would be wrong. And there will be questions on the first exam, and those may show up on the final again, where I am specifically testing you on significant figures. If I say, do the problem and express the answer to the correct number of significant figures, 45.0 would be wrong. Yep.
So then, since it's not exactly 45, would we need to put approximately?
That's a good question, because when we look at whole numbers, we tend to think of them as exact numbers. What they've done here, which I'm not real happy about, these are all implied to be measurements. There should be a unit here. So if this was 45 meters, then we would see clearly that this is not a counting number. But when a scientist looks at a number like 45, we're going to assume uncertainty in the last digit, whether that's the ones place or any other place.
So you're already assuming it's approximate, basically.
Yeah, we would assume that it's approximate. Where we would know that it was not was if it said 45 cars. Okay, 45 cars, you could count 45 cars and be exact. And so then you would recognize it as an exact number, but otherwise not. So in the absence of a real clear suggestion that that's a counting number, you should assume that it's not a counting number. And don't be tricked into thinking that all whole numbers are exact numbers, because they're not. Okay, let's do this next one. So here we have numbers being divided. The rule is the same. We have to look at each number and find out how many sig figs there are there. 5.892. How many? 4. So this has 4. 6.10 has 3. 3 is smaller than 4. So our answer then should have 3. So we're going to keep the 9, the 6, and the 5. We need to get rid of the next one. We're going to get rid of the 9. 9 is 5 or greater. We need to round up, because this number is closer to 0.966. So we're going to express this as 0.966 with 3 significant figures.
Is it crucial that we put the 0 before the decimal?
It's not crucial. I think it's a good idea because when you're handwriting something, decimal points sometimes get lost, especially with a pencil. You made the decimal point, but it was so faint that the person looking at it isn't going to see it. If you put a 0 in front of it, they're going to go looking for a decimal point. Because why, if it was 966, why would you put a 0 in front? You wouldn't, right? So and here on the example, I should probably go change this. There really should be a 0 there. Because that's pretty much the standard thing, is that it's 0 point whatever.
So would you cross that on a test if we forgot to put the 0?
Nope. Nope. Definitely not. Now, if you wrote 0.965, that's wrong. See, I like the math part of chemistry because I like things where there's one right answer. I know I was right. And I understand that a lot of people don't like that. So you have my sympathies on this, but this is one of those places where there's one right answer. Okay. So I mentioned this already, but here's the official slide for rounding. You're only going to look at the first digit being dropped to decide whether you're going to round. I sometimes get a student who, they've got a number like this. Let's see. Oops, I have to tell it to annotate. 4.736729. And they're trying to cut it off here. And so then they're going to take the 9 and they're going to say, well, that rounds up to a 3, and this rounds down to a 7, and this rounds up to a 7, and that rounds up to a 4. No, don't do that, okay? It's way too much work, and it sometimes gets you the wrong answer. Ignore all these guys. They don't matter. Just look at the first one. If the first one is 4 or less, you round down because it's closer to the lower number. If it's 5 or greater, you round up. And we're going to not do the odd even thing with the 5s. We're just always going to round up 5. Only round the final answer. Okay? Let's go ahead and do these examples. Perform each calculation to the correct number of significant figures. So first, just do it on your calculator. So 1.01 times 0.12 times 53.51 divided by 96. And you press equals. Oops. Come on. My calculator is telling me 0.06755,638. Did anybody else get that number? Okay, good. So here's the thing about calculators. It's really easy to push the wrong button. And some of these, there's a lot of digits and a lot of operations, and it's very easy to do one key wrong. Maybe you touched the button, but you didn't push it hard enough, or you pushed it too hard and it went twice. So I would encourage you to always do your calculations twice. If you get the same answer, you're either really consistent in your mistakes, or most likely, you got the right answer. And so in class, I'm going to do it once, but I'm going to ask for confirmation from somebody else, because I make mistakes up here. So we're going to do it on the calculator. We're going to write down everything the calculator shows us. Now, some of your calculators may show you more digits or fewer digits. That's fine. But just write it all down. Now we're going to look at the significant figures. And it's multiplying and dividing. So we go over and we look at the first one, 1.01. How many sig figs? And 0.12. How many sig figs? 2. 53.51. 96. 2. We can't assume that that's a counting number. So the smallest is 2. Initially, you should probably go through and write all these down, like I'm doing. In the future, you'll just be able to go back and look, oh, the smallest one is 2. I'm going to round it off to 2. These zeros are leading zeros. Those aren't counted. So we're going to keep the 6 and the 7. We're going to keep 2 digits. And then we're going to look at the next one, 5 or greater. We need to round up. So 0.068. That's our answer. I think it's good to be in the habit of writing down the whole number and then rounding it. Because then if you rounded it incorrectly, we can still see, oh, there, she had the right answer there. She just rounded it wrong. Let's do the next one. 56.55 times 0.92 divided by 34.2525. And I'm getting 1.518899643. Anybody else?
Yeah.
Yep, okay. Write it all down, then let's go back and look. Which of those has the smallest number of sig figs? The 0.920. How many does it have? 3. So that means we're going to keep 3. I'm going to keep the 1. I'm going to keep the 1, the 5, and the 1. And I'm going to get rid of the 8. I don't care what these guys are. It doesn't matter. It's garbage. And so this is going to round up, and this is going to be 1.52. Any questions? This is one of those things that you have to go home and practice. The sooner you do it, while it's fresh in your mind, the more likely you are to remember it. So there's studying smart and there's studying hard. Study smart. Okay, so that's more than enough for today. I'll see you on Thursday.